Am I audible? I think I must be audible. It's the same configuration as yesterday, so I don't think there should be any problem. Fine. So I'll be starting from the last part of lecture 28, which has electromotive force in it. I think until here it was minor 2, I think, but I'll just start from electromotive force. Hmm. Electromotive force. Can I write? I can write. Fine. It says electromotive force, but it's not actually a force. It is like it has the same units as voltage. So its units are like voltage. It's called, okay. First we'll see what is electromotive force, and then we'll try to understand why is the name force given to it. Current flow of charges same along the loop. Okay. Mm, okay, fine. What is in this picture? There is some potential difference. Uh, there is some positive potential here and negative potential here. Hence, there is a potential difference because of which uh, current will go from positive to negative. That is fine. What they're telling in this slide is there will be no piling of charge carriers in any place in the wire. Piling up in the sense no charges will go and accumulate on uh, in any place, no corners or nothing, because one study found out that not found out, they proposed this theory. It's like uh, yes, so automatic self-correcting system. What do they mean by this is let's suppose uh, let's suppose the charges pile up somewhere in the wire. When they do that, what's going to happen? You will create a new electric field because you have charges piling up, so you'll have an electric field. What does this new electric field do? Or just think of them as uh, charges accumulating somewhere. So there is some collection of positive charges. Positive charges because I'm considering my charge carriers to be positive. What would this do? This will start slowing down the incoming charge that is coming in because positive will repel. So this will slow down. Whatever is coming in will slow down. On the other hand, whatever is going out will also get repelled because positive repel each other. So this will go faster because while going out, it's getting repelled, so it will go out faster. But whatever is coming inside will come inside slowly because it's getting repelled. Repulsion is in the opposite direction of uh, this direction. It's going inside, right? So it's going to slow down. So slowly, over time, what's going to happen? Not over time, but this all of this happens instantly. That is what they're trying to tell us. Uh, when outflow is more than inflow, finally what will happen is these accumulated charges will also leave. So finally, after all this, what's going to happen is there will be no accumulation of charges. That is what this slide is trying to tell us. And all of this happens almost instantly. So we don't have to consider any piling up of charges when we are talking about wires. When there is a current, it's there is uniform current with no piling of charges. Mm, At this point, they're just trying to note down. They're just trying to note down the net electric field. Electric field is nothing but force per unit charge, right? So this is some force per unit charge. This force per unit charge comes from the battery, because whenever there is a potential difference, all the charge carriers will start moving. So why do they move? Because some force is applied on them. So, and that is the electric field. So electric field is the force per unit charge that acts on the charge carriers whenever there is a potential difference. So they're just trying to write down the uh, net electric field or net force per unit charge. So they're saying this is due to, I don't know, it could be due to the battery or whatever. Yeah, yeah, you have battery is a chemical force. This is like if you uh, you can Google this. It's like, okay, it's given here. Mechanical pressure converted to electrical. That is also right. You have multiple ways of generating electricity. Basically, if you have a potential difference, then you can generate electricity. And that this extra E is this one, the piling up of charges, the electric field generated due to the piling up of charges. So that is that E. Now they're trying to see what is this F bar dot dl bar going to give. This F bar is basically the net force per unit length. Force per unit length. So if they integrate it along the length, they will get the net force, right? Force per unit charge, my bad. So this is force per unit charge. So if they integrate it along the length, what will you get? What will the units be? Newton per coulomb meter. Newton per coulomb is Newton meter is joules. Joules per coulomb is volt. So finally, you're getting volts at the end of all of this. So at the end, whatever you get, and okay, before that, this is actually zero, right? Because uh, is it zero? Yes, it is. I think we discussed, right? There will be no accumulation of charges. So that electric field is going to disappear. The electric field due to the accumulation of charges, that is going to disappear. But there is another electric field that is due to the potential difference that you have. So that is still there. So this E is due to accumulation, and this E is due to the potential difference. Okay, so how do we write the potential difference? If you remember, uh, VAB is nothing but VA minus VB, and how can I get this? I can get this from there is this gradient theorem, no? So I what was that? Does anyone remember Stokes theorem? or gradient theorem for that matter. Okay, fine. I got the gradient theorem. Electric field is nothing but negative of gradient of potential. Here E is a vector quantity, V is a scalar quantity. So if I write E dot dl, it is nothing but negative a gradient of V dot dl. Let's say it's from A to B. This is also from A to B. Then, okay, I need some space. This would mean this is, I have to apply the gradient theorem here. So if I apply the gradient theorem, I will get negative of uh, VB minus VA. So this is, what is this? This is VA minus VB. So this is VAB. So VAB is here VAB is integral A to B E bar dot dl, but here they've given minus. So who is right? Either the slide is right or what I wrote is wrong. No, either the slide is right or what I wrote is right. Give me 1 minute. Let's see. Just 1 more minute. Then we'll just move on. Wait, let me have a rough sheet somewhere. Fine. I was telling that E is minus gradient of V. So E bar dot dl bar from A to B should be nothing but minus A to B gradient of V dot dl. There is something called the gradient theorem. If you use that, you will get V at B minus V at A. This is nothing but VA minus VB. So if you're finding the potential difference between 2 points A and B, This is at VA, this is at VB. So potential difference, so VBA should be VB minus VA. Is it this one or is it this one? I think it's the first one. Mm, am I missing anything? I don't think so. Maybe this is what it is, but oh wait, the slides could be wrong. I shouldn't, because if I open this, wait, I can't read. If I open this, I will get gradient of V dot dl. So minus VB minus VA, which is VA minus VB. Okay, I got VAB and V. Okay, this is VAB, correct only. Then where am I going wrong? No, 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 no. Here, minus of minus. But VB minus VA is VBA, not VAB. So I don't think this is right. I don't think this is right. We'll see. We'll see later. But I don't think that is right. I don't think the minus sign should be there. Mm, okay, so finally this integral is giving us some voltage, some sort of voltage. So we'll see what is that. Okay, we'll see. We'll just continue with the procedure. Considering a conducting rod moving with a velocity v. Okay, I have a rod that is moving with a velocity v in a uniform b. Okay, b is coming out of the page because if you have dot and circle, it's coming out. If you have cross and circle, it means it's going inside. So you have to use your right hand to see in which direction will the magnetic force be. So if you point your you can use your right hand rule, whatever right hand rule you remember, you use it. What I will be using is uh, there is one easy way. So what you do is, let's say you have your hand. Let's say this is your hand. Okay, fine. It, it, uh, this is better. Let's say you have a hand. You point your fingers, all your four fingers, in the direction of the magnetic field. First do that. So in this case, your four fingers will point towards you because out of the page. So four fingers are pointing towards you. And then you point your thumb finger in the direction of velocity. This is your right hand. When you do that, your palm will, the direction of your palm will give you the direction of the force. In this case, your if you use this right hand rule in this picture, your four fingers will be pointing outside the page. Your thumb will be pointing in the direction of velocity. Finally, your palm will be facing downwards. So we got the direction of the force. Now, from where are we getting all of this? From this equation, we know that force force due to magnetic field is nothing but Q into V cross B. So V cross B, there are multiple ways of finding the direction of V cross B. One simple way is simply uh, taking your index finger, putting it in the V direction, then taking your middle finger and putting it in the in the direction of the magnetic field. Then finally, your thumb will give you the direction of the force. This is one right hand rule. I gave you one more right hand rule. It's still the right hand rule. I feel this is easier in some cases, or else you can use this also. That is also fine. So point this one point. What do you point? You point your fingers in the direction of the magnetic field. Then you point your thumb in the direction of the velocity. Then finally, the palm will give you the direction of the force. So here I got the direction of the magnetic force, which is downwards. So what does this mean? All my charges in this rod will start going down. And when they start going down, all positive charges will start getting accumulated here. Likewise, there will be negative charges because positive charges will experience a force in the direction of the magnetic force because Q is positive there. If Q is negative, then you will experience force in the opposite direction. So all negative charges will go up and positive charges will go down. Finally, uh, what will happen is since positive charges are down and negative charges are up, you will get an electric field between them. So this is one more force. Now one more force is coming into picture. Electric field is coming into picture. Finally, all charges will stop moving when there is an equilibrium between the magnetic force and the force due to electric field. Force due to electric field is simply Q times electric field. So this is not equal to V. This is when force of electric field is equal to force of magnetic field, which means when QVB, here V and B are perpendicular, so VB sine 90, fine, I'll write that as well, is equal to electric field. Electric field is QE. So finally, you'll get E is equal to VB. So this is the equilibrium condition. In equilibrium condition, no charges will move, but there is a potential difference now. Here all positive charges are there, here all negative charges are there. And all of this is only when the rod is moving. If the rod is not moving, then V will be zero and there will be no force. If there is no force, then charges won't move. If charges won't move, there will be no accumulation of charges. If there is no accumulation of charges, you will not get any electric field. Mm, okay. So, and if the rod is moving with velocity v, you will reach some equilibrium point. You can't keep increasing the e. Finally, one e will come. that E will be equal to V times B. You can't get more than this. This is the limit. It will stop here. So it's like you created a battery at this point, because if you have electric field, essentially you created a potential difference. This is at a positive potential, this is at a negative potential. That is what batteries have, right? In batteries you have a positive potential, you have a negative potential. The only thing that's remaining is if you join this with a wire, you will have electricity. So if you have potential difference, you join the different terminals with a wire, you get electricity. Electrons will start flowing. Here that wire is not there as of now yet. Maybe we'll see if we'll add, if we will make put include this in a closed loop, we will see. I think that's in the next slide. Where is this? Okay. Hmm. Okay, we've seen this. This person is using the normal right hand rule, I think. Oh, this is the other version. What you do is mm, the other version, in the sense, this is very similar to the no. I mean, no, it's difficult. I can't show you my hand now. So uh, just imagine. I think all of you would know right hand rule, so I don't have to explicitly mention that. Fine. So considering the rod. Okay, see, they've corrected it. So electric force equal to magnetic force. Nice. So here, what is important? You have to see in which direction things are moving. So velocity is in this direction. Magnetic field is coming out of the plane. Now you have to see in which direction is the magnetic force going to be in. We know magnetic force is Q into V cross B. So find the direction of V cross B. We know direction of V. We know direction of B. Find the direction of force due to magnetic field. Their directions exist because they're all vector quantities. That's why I'm writing this bar over them. Q has no direction because it's not a vector quantity. Charge is scalar. Mm, fine. So equilibrium happens. No more charge will accumulate because equilibrium means nothing will move. Okay, this is what I was talking about. You point your fingers in the direction of the magnetic field. You point your thumb in the direction of the velocity. Your palm will give you the direction of force due to the magnetic field. And this is general for if you have any, uh, let's say you have A bar is equal to B bar cross C bar, then here B can be replaced with C, V can be replaced with B, F can be replaced with A. So it's you can use this rule for any cross product to determine the direction of a cross product between two vectors. So this will be the fingers, this will be the thumb, this will be the palm. Using this, you will be able to determine the direction, the final direction, the resultant direction. Okay, did anything change here? No. B is pointing outwards, B is right side. So finally, palm will give you downward direction. That means magnetic force due to magnetic field is downwards. Fine, they were like charge. They are like charge carriers, right? So if it's positive charge carriers, what will happen? All positive charge carriers will go down. If it is negative charge carriers, they will all go up. In both the cases, the scenario is the same. What is it? The electric field is uh, in what direction? This direction. Electric field is from positive to negative, right? So that will be the direction of the electric field. Yes, so don't forget. Positive to negative will give you the direction. Positive to negative or negative to positive? No, no, no. Positive to negative is the, we know that E bar is negative of gradient of V. So this is at a higher potential, this is at a lower potential. So gradient of V will give you downwards direction. So okay, yes, so electric field will be in this direction, upward direction. Electric field will be in the upward direction, yes. See, even if you forget the directions or if you're confused, you can use the existing formulae to determine where is where. So since electric field is in the upward direction, force due to electric field is also in the upward direction. That is why you will reach an equilibrium. Force due to electric field. So both of these forces will cancel, and you will. This is when equilibrium is attained. So no more charge accumulation. What I was telling is, if the charge carriers are electrons or protons or whatever, positive, negative, final story is the same. What is happening? If you have positive charge carriers, they're all accumulating down. If you have negative charge carriers, they're all accumulating at the top. But the story is the same. You have uh, potential difference is same, because if I say this is VA and this is VB, this is VB. Let's say VB is 0 and VA is let's say 10 volts. And let's say VA is 0 and VB is minus 10 volts. So what is VAB? VAB is VA minus VB, which is 10 volts. What is VAB here? VAB is VA minus VB, which is also 10 volts, minus of minus plus. So the story is same, irrespective of the sign of the charge carriers. The electric field is in the same direction, which is upwards. If electric field is in the upward direction, potential difference will be in the other direction. Because what is the direction of potential? I mean, the gradient of the potential. It goes from smaller potential to higher potential. That will be the direction of the gradient of the uh, potential. Potential in the sense this one. Here V is the scalar field, the potential. So if E is upwards, then gradient of V will be downwards. Only then minus of down will be upwards, if you get my point. Anyways, so irrespective of the charge carriers, you will get the same electric field. Mm, yes, so they were asking this question. It's the same thing. But in that case, what will change is the directions of the forces. So in that case, the magnetic force will be upwards, force due to magnetic field, and force due to electric field will be downwards. But the net effect is the same. You will have electric field in this direction, upwards direction. Electric field is upwards, but force due to electric field is downwards. Why is that? Because Fe is nothing but QE. Here Q is negative when charge carriers are negative. That is why force due to electric field will be in a direction opposite to uh, will be in a direction that is opposite to the electric field. So Finally, net effect is same. Electric field will be in the same direction, irrespective of the charge carriers here. Mm. Okay, if the conducting rod is moving, if it moves to the left, so you have a conducting rod, it's going to the left. Magnetic field is still coming out of the plane. Then what will happen? Same story. Use your right hand rule. So your four fingers will be pointing out of the plane. Your thumb will be pointing towards the left. So your palm will be pointing this way. So that will be the direction of force due to magnetic field. So that means if there are positive charge carriers, they will be accumulating on the top. If there are negative charge carriers, they'll be accumulating at the bottom. This will create an electric field in this direction. So positive charge carriers will experience a force in this direction. So force due to electric field will be here. So here electric field is in this direction. So here there is a higher potential. Here there is a high potential. Here there is a low potential. Yes. So this is happening. This is what is happening. Okay. Interactions of a changing magnetic field with stationary charges. Interactions of a constant magnetic field with moving charges. Fundamentally, there's no difference. Okay, we'll see. Okay, so here now there is no rod, there is a closed loop. So, will there be electricity? We'll see. Will there be current? Will there be flow of electrons or flow of charge carriers? We'll see. Consider instead rectangular conducting loop. So if you look at only this portion, this part is basically the rod that we were dealing with in the previous cases. So let's do the same process. B is pointing outwards. B is outwards. B velocity is in the its right side. So using right hand rule, we'll be able to know that the force due to magnetic field experienced by a positive charge carrier will be downwards. Your palm will give you the direction. Remember, there is if this is velocity, first you point your fingers, magnetic field. Thumb will give you the direction of velocity. Finally, the palm will give you the direction of the force because of this equation, force due to magnetic field. If q is negative, then force direction will change. It will go backside. So careful. This is if q is negative. This is for positive q. This is for negative q. So careful. Oh, careful in the sense we're assuming there are positive charge carriers, but we've seen this. Irrespective of the charge carriers, the effect is the same, so there is no problem. The only problem is the direction of the forces will change. That's it. But the net effect, which is the electric field that is being induced, that is the same. That is in the same direction. Anyways, so a magnetic field is not magnetic field. Force due to magnetic field is downwards. That would mean charges will try to go this way, positive charges. If there were negative charge carriers, they would have gone upwards. But they won't accumulate there because now you have a conducting rod. So there will be no accumulation. We've seen that if charges try to accumulate anywhere in any of the corners or any place, there is a self-correcting mechanism. So it will automatically start moving if there is it's like if it finds a way to go somewhere, it will go there. So finally, what will happen? No charge will be accumulated. You will get a current. You will get a current. So charges will move in a loop now. So this portion of the loop is acting like a battery now, because what is a battery? You just have potential difference. Here you have potential difference. So this part is acting like a battery. So you'll get some current. Okay, now what about this portion of the rod? I mean, If I take this small portion, this is also like a rod. So here also you will get this is also moving with velocity v. So here also you will get charge accumulations, but they are so small. They're so small, like the rod is so thin, so this effect will not be considered. Here also you will have small uh, accumulation. So you'll have negative, 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 positive, 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 positive. But there, since the rod is thin, that effect is not considered. So we will our assumption is going to be that nothing happens in the horizontal portions of the rod. Only the vertical portions of the rod, something is happening there. So nothing happens in the horizontal portions of the rod because it is a thin rod and the charge separation will not be too much. So the effect of uh, EMF. So this phenomenon is EMF. So you're inducing some. We will see. We'll come to that. We'll see. Inducing in the sense here due to uh, see there is a conducting rod that's moving in a magnetic field. We will come to the EMF part later, but we'll just go on with this. So you'll have current here. Until how long will you have current? Now they have other cases. Okay, yes, they have other cases. Fine. The current will not stay for long. The current will stop soon. We will see why. But let us read what they're trying to tell us. Mm, no, they don't get accumulated because they can start moving now. They have a lot of space to move. Mm, yes, because the rod is thin in horizontal. The horizontal rod is thin, so we can ignore the effects of that. Okay, let's see. So this is something very similar because now you have a magnetic field in the upward direction. So you can point your fingers in the upward direction. Okay, there's no velocity. So if there's no velocity, then directly you can say force due to magnetic field is zero. So nothing will happen there. No current is there. In this case, B is upward. So you point your fingers in the direction of the magnetic field. Point your thumb in the direction of the velocity. That would mean the palm will give you the direction of force due to magnetic field. So that would mean the charge carriers experience a force in this direction. Positive charge carriers experience a force in this direction. That would mean you will get a current. So positive charge carriers will try to go this way. They will come here. So there is a current. There is a clockwise current. There is a clockwise current. Now in the other case, direction of the magnetic field is still the same. V is this way. So if V is this way, that means now you'll have to flip your arm. So four fingers are there, thumb is this way. So your palm is there in the front. So this is the case. This is your right hand. So the palm will give you the direction of the force. Mind you, we are assuming they are positive charge carriers. If it's a negative charge carrier, then you have to take the direction that is opposite to the palm. So behind the palm. But we've seen again. I'm telling this again. We've seen that in both the cases, when there is a positive charge carrier or when there are negative charge carriers, the net effect is the same. The direction of current is not changing. The net effect is the same. If you want, we'll try that as well. So here forces in the other direction, the direction of the palm. So plus plus plus, they will keep going this way. So you get a current. So here current is in the clockwise direction. Previously anti-clockwise. Now it's clockwise. Fine. If there were negative charge carriers, what would have happened? If there were negative charge carriers, force would have been in the opposite direction. So minus minus minus. Minus is going in the anti-clockwise direction. But we know that current is the direction of the flow of. So current is basically the flow of positive charge carriers. So if negative charge carriers are going in anti-clockwise direction, it is considered that positive charge carriers are going in the clockwise direction. So we got the same, see, we got the same thing, same result. When they were positive charge carriers, the current was flowing in a clockwise direction. When there are negative charge carriers as well, the current is considered to flow in the clockwise direction, because current is always a measure of flow of positive charge carriers, not negative charge carriers. Mm, okay, this current is called induced current. Induced because it came from, see, here we are not having any battery or something. We are simply moving the wire in the presence of a magnetic field. So this current is induced by the magnetic field. What is the difference from, that's what, in regular current you have some potential difference because of which electrons start moving. But here they are moving because of induction, electromagnetic induction. Electromagnetic induction. Yes, electromagnetic induction. Yes, electromagnetic induction. Okay, so now we will finish the story that we started. We were here, no? We were in part one. There is part two, part three, part four. So in part one, what happened? We'll consider positive charge carriers. Uh, what is happening to positive charge carriers? Velocity is in this direction. A magnetic field is coming outside. So the direction of the palm will give you the direction of the force due to magnetic field. That would mean plus charges want to come this way. So they have all this space to go. So you get a current in the clockwise direction in this case. This is part one. Part two, what is happening here? Same story. You have velocity here, magnetic field out coming out of the plates. So plus plus. So magnetic I mean, positive charge carriers want to move in this direction. But if you notice, now even this vertical rod, even this can be considered as another vertical rod. So if you consider velocity this way and magnetic field outside, so force is again downwards. So you will get plus plus here as well. But where should this plus plus go? It will go in the other direction now because that is the only empty space it sees. So if you look at this, plus plus are clashing, right? So you won't get any current in this case. Now you can consider this to be a battery, right? So this is a higher potential, this is a lower potential. You can consider this to be another battery, higher potential, lower potential. Now what do you think is going to happen if my circuit looks like this? Let's say they have the same voltage. Will I get any current? No, you won't get any current because these two will cancel each other. So the same thing is happening here. These two are cancelling each other. So you won't notice any current here. No current. You can't measure. Okay, why resistor? I'll put an ammeter. You won't find anything. Put an ammeter. So no current. You'll get 0 amps. No current. That is part 2. Part 3. Part 3 is basically part 1. But the thing is now the battery, this battery is over now. You won't get any electric field here because there is no magnetic field there. If there's no magnetic field, then uh, you won't get any force experienced due to magnetic field. If there is no force experienced, then charges will stay wherever they are. They won't go anywhere. But the rod on the left side, what is happening? Velocity right side, magnetic field out of the page, so force downwards. Positive charge carriers experience a force downwards. So plus plus, they're trying to come down. So now it can freely go do a tour. It will just go around and come back. So there is current at this point. Here there is anti-clockwise current. Here there is, oh, this is clockwise. This is clockwise current. This is anti-clockwise current. So if you notice, the directions of the current have changed. So here no current, yes current, no current, Yes current, no current. Nice. So this is the generic way of finding the direction of the force. I mean, this is essentially what we're doing, no? Thumb is pointing V. You just open all your fingers and point it in the direction of the magnetic field. Then your palm will give you the direction of the force, and therefore the current. It's the same thing. Here, the direction of the force experienced by a positive charge will give you the direction of the current, because current is considered to be the flow of positive charges. So if you notice, the current is basically in the direction of the in the direction of the magnetic uh, in the direction of the force due to magnetic field. FB is downward, so current is also going like this. Same story. And clockwise current, anti no current, anti-clockwise current. So this phenomenon is called electromagnetic induction. So there is a more formal definition. We'll see it. Now the other idea is, now there's something called magnetic flux. It is given by B dot dA. So this is called magnetic flux. There is something called electric flux as well. That is just E dot dA, but I don't think we use this anywhere. But I wonder, maybe somewhere. But we are concerned about magnetic flux. If you notice, all of these are closed loops, right? So I can define area vectors that is perpendicular to each of these areas. And here magnetic field is outside, so fine. So for each one of these loops, I can define magnetic flux. Magnetic flux is basically B dot dA. Here B is 0 outside, but here B is not 0. In this in this area, in this region, you have magnetic field. Fine. So magnetic flux. So electromagnetic induction is described in terms of magnetic flux. We'll see how. So if you notice, when this loop is entering the region of uh, magnetic field, what is happening is this magnetic flux it's increasing. Magnetic flux is increasing. Why? Because as the loop goes inside, more and more of its area will uh, uh, more magnetic field lines will start passing through the area of this loop. So magnetic field lines, in the sense, the magnetic field is described as it's like you have field lines passing through. Uh, See, I think you remember, right? We represented. Let's say I have a positive charge. I represent the electric field like this. I simply draw lines, right? So those lines are called electric field lines. Similarly, we have magnetic field lines. So this magnetic field is basically, you have field lines across the region of this magnetic field. So this flux is defined to be the number of field lines passing through the area. This magnetic flux is defined to be the number of field lines passing through a certain area. So this B has another name. It is called magnetic flux density. It will give you the number of field lines per unit area. So number of field lines per unit area into area will give you the number of field lines. So flux will be the number of field lines, magnetic field lines. So essentially, when the loop is going towards the right, more number of magnetic field lines will enter the area of the loop. It means magnetic flux is increasing. In the second case, magnetic flux, there is no change in magnetic flux because at every instant of time, the same number of field lines are passing through the loop. So there is no change in magnetic flux. In this case, magnetic flux is decreasing because as time passes, the number of field lines passing through the area of this loop is decreasing. So here magnetic flux is decreasing. So the observation is this: you will only observe a you will only observe a current when the magnetic flux changes with respect to time. That is in this case and in this case. So current was not observed in any of the five cases except the second case and the fourth case, because those two cases were the only cases where magnetic flux changed with respect to time. This was the observation by Faraday. So Faraday tried to explain this current in terms of magnetic flux, change in magnetic flux. Now you have to use your right hand again now in order to get the idea, to find out the direction and things. So I will draw one more hand here. So what you do is, let's say you have your hand, your right hand. This is your thumb, and your right hand looks like this, right? Yes, this is your right hand. Right hand. This is your thumb. Could be a better hand, but anyways. Hmm. So what you do is, okay, first let us, they did not give us the direction of the magnetic field. Let us see what is the direction. We can find the direction ourselves. They told velocity is right side and current is this side. So guess what is the direction of the magnetic field? Is it into the plane or outside the plane? Maybe if we, okay, I will show you the previous example. Maybe here magnetic flux is increasing. Here magnetic flux is decreasing. So what you do is you take the thumb of your right hand and point it in the direction of the magnetic field. That would mean outside, right? So the thumb magnetic field is out of the plane, so thumb will point towards you. Okay, fine. So here magnetic flux is increasing, right? So if magnetic flux is increasing, what Faraday observed is this one: if magnetic flux is increasing, what the loop will try to do is the current will be induced in such a way that it will resist the change in magnetic flux. So how can it resist the change? It will generate uh, what do I say? It will generate its current in such a way that it opposes the change in magnetic flux. So what does that mean? Mm, how do I say this? Okay, do you guys remember this? In minor 2 portion, we saw that the simplest configuration of a magnet is basically a current in a loop. So this is basically a magnet. if a current is there in a loop, that essentially produces a magnetic field. So what will this loop do is it will produce a current in such a way that the magnetic field that is coming as a result of this induced current, that will oppose the change in magnetic flux. So in this case, when magnetic flux is increasing with time, the current induced produce will be generated in such a way that the resulting magnetic field will oppose this change. So how do I oppose the increasing flux? So magnetic field will be how do I say this? So basically, it will be generated in the opposite direction. So is magnetic flux is increasing in which direction? It is increasing in the outward direction. So in order to decrease this one, an opposite magnetic flux will be generated. So how do I check the direction? If it is if it is increasing in the out of the plane direction, you have to increase it in the into the plane direction. This is what is happening. Uh, how do I say? Okay, I'll write this as this is the cause. Something is happening. The effect is this one. You're increasing magnetic flux in the outward direction. So the effect is magnetic flux will be generated in the opposite direction as well. That will be into the plane. So what you do is you take the right hand of your thumb and point it in this direction. Take the right hand of your thumb and point it in this direction. So into the plane means your thumb is now pointing into the plane. And what you do is now you curl your fingers. So you have the other four fingers, right? Just curl them in the direction. Just rotate your four fingers. That would give you the direction that looks like this. It will give you the clockwise direction. When you point your thumb into the plane and when you rotate your four fingers, you will get the clockwise direction. So that direction represents the direction of the induced current. So in this case, if you notice, the direction of the induced current is clockwise. So I will tell again what is happening here is magnetic flux is increasing. Where is it increasing? It is increasing in this direction, out of the plane. It is increasing in out of the plane direction. So what will the loop do? It will induce a current in such a way that in the opposite direction also the same thing is generated, so that the net is cancelled. So how is that happen? How does that happen? If out of the plane it's increasing, then into the plane it should increase. Or in other words, out of the plane should be decreased. So that is also equivalent to that. Decrease in out of the plane. How do you decrease in the out of the plane direction? Basically, you increase in the into the plane direction. So you take your right hand of your thumb and point it in this direction into the plane and rotate your fingers. You will get the clockwise direction. If I repeat the same exercise here magnetic flux is decreasing. In what direction is it decreasing? Magnetic field is out of the plane. Magnetic field is out of the plane. So in that direction it is decreasing. So what is actually happening? It is decreasing in out of the plane. So what will the loop do? The loop will do the exact opposite. It wants to resist the change. So you'll have to increase it in the out of the plane direction. So if you want to increase in the out of the plane direction, how do you do that? Take your right hand of the thumb and point it in this direction. So out of the plane means it is out of the plane. You take your thumb and now you rotate your fingers. If you rotate your fingers, you will get the anti-clockwise direction. So that is the direction of the induced current. Now we'll see. Now we'll see in what direction should the magnetic field be. That like the induced current is in the clockwise direction, right? So that would mean your right hand thumb should either your right hand should be placed in such a way that when your fingers are rotating, they rotate in the clockwise direction. When you do that, your thumb will automatically point uh, into the plane. So here magnetic flux is decreasing. What is happening? This is happening. I don't want to write cause though. It's not cause effect. It's like what's happening. What's happening? Flux is decreasing. In which direction you don't know. But then the result is current is induced in clockwise direction. Current is induced in clockwise direction means your thumb is pointing into the plane. Your thumb is pointing into the plane means in that direction the magnetic field is being produced. It means it's trying to produce a magnetic flux. It's trying to increase magnetic flux in this direction into the plane. So why would it do that? Only if it wants to. Why would it do this? Only if it wants to negate something. So that means something that is opposite to the result is happening. What is opposite to the result? Uh, Opposite to the result is magnetic flux is decreasing in the direction into the plane. So the direction of the magnetic field is into the plane. So they gave us I, they gave us V. We could, they should have given us B as well, but whether they gave us that piece of information or not, we were able to figure out what is the direction of B. If you want, you can start the process uh, from the starting. Now that we have our B, we can start from there. So what is happening? Now we know magnetic field is into the plane. Now we'll try to find out the direction of current. So when this loop is moving outwards, magnetic flux is decreasing because number of field lines passing through this area is decreasing as time passes. So what is happening now? Uh, Flux is decreasing. In which direction? Into the plane. Into the plane is basically this one, right? So I will magnetic flux is decreasing in the into the plane direction. Then what will happen? Then the loop will try to increase the magnetic flux in this direction into the plane. So what does this mean? Thumb will point in the into the plane direction. Then fingers will give you the you rotate your fingers. So rotating fingers will give you the direction of the induced current. If you rotate your fingers, if you curl your fingers, they will rotate in the clockwise direction. So that is how I is in the clockwise direction. In the other case, when the magnetic field region itself is being pulled to the left, what is going to happen? Even in this case, magnetic flux is decreasing. So experiment 1 and experiment 2 are the same things because magnetic flux is decreasing in which direction? Magnetic flux is decreasing in the into the plane direction. So now what will happen? In order to oppose this behavior, magnetic flux will be generated in the it will try to produce a magnetic field such that the magnetic flux is increased in the opposite direction. I mean, if it is decreasing in one direction, the opposite thing is to increase it in the same direction. If flux is increasing somewhere, isn't there anywhere? Okay, we'll see. If flux is increasing, okay, we'll come to that example. Here, flux is decreasing. So the opposite effect is you increase the flux in the same direction. If you increase the flux in the opposite direction, it will the effect will be cumulative. It will not be the effect will not be negated. Finally, what you want is both of them should be like canceling each other or something like that. So if flux is decreasing in into the plane, the opposite effect is flux will be increasing in the same direction. That would mean my thumb will be pointing inwards into the plane, and my fingers will be rotating in the clockwise direction. That's why I is also in the clockwise direction. Let's say, okay, now let's assume B is increasing. If B is increasing, that means my magnetic flux will also increase with respect to time. So if B is increasing, what's going to happen? If B is increasing, then let me write. If B is increasing in the into the plane direction, then the opposite thing that you could do is decrease it in the same direction. But what do you mean by decreasing in the same direction? It means you want to increase the flux in the opposite direction. Now you take your thumb and point it in the out of the plane direction. So here B is increasing. So what's the current going to be? So you take your thumb and point it in the out of the plane direction. If thumb is pointing in the out of the plane direction, your right hand thumb. So if you try to rotate your fingers, if you curl them, what is going to happen? You will get an anti-clockwise direction. So that will be the direction of your eye. In this case, they did not tell if B is increasing or not, but by looking at the direction of I, we can understand that in this case B is decreasing, and hence magnetic flux is decreasing. So if you get this point, you'll be able to answer in which direction is the I induced. I think there were questions regarding that. Maybe in the next. Uh, okay, so mathematically, d phi by dt will give you the rate of change of magnetic flux. D phi by dt is basically rate of change of magnetic flux. The minus sign uh, signifies the opposition. Basically, the loop is trying to oppose it, right? So the effect of the loop is the opposite of the rate of change of magnetic flux. That's why you have a minus sign. So whatever the loop is doing, it is trying to oppose the change. So that's why you have a minus sign here. This epsilon is called the electromotive force. If you do dimensional analysis, you will realize this has the unit of volts. So it has the same potential, it has the same units as a potential difference. And you know, if you have potential difference, then you have current as well. So that's there. But here we are not using any potential difference. Here there is, this is induced just because This is a phenomenon, electromagnetic induction. So, induction of current due to change in magnetic flux is called electromagnetic induction. And this epsilon is called EMF, electromotive force. Its units are volts. It is a measure of the rate of change of magnetic flux. Fine, there are more examples here. Okay, just it's the same example, right? Now we can try to answer this question using the concept that we just saw, change in magnetic flux. As the wire is moved towards the right, the number of field lines passing through the area of this loop decreases. So that means the magnetic flux is decreasing in this direction. But electromagnetic induction, what does it state? It is a phenomenon in which the loop opposes the chain, right? So the loop will induce a current in such a way. Okay, anyways, so you people know this, right? If there is a loop with current I, there will be a magnetic field around the wire, right? And the net magnetic field will look like this. How will it look? It will look like this, right? I think it will look like this. You can just Google this. Magnetic field around coil. It will look something like this. So finally, what I'm trying to tell is the magnetic field will be in this direction. So if you take your right hand and point your thumb in the direction of the magnetic field, and you have your right hand, right? Try to curl your fingers. If you try to curl your fingers, they will fold inwards, right? They will fold inwards. So this will give you the direction of the current. So that is the relationship. You have a magnetic, you have a current carrying loop. If you have a current carrying loop, you will also have a magnetic field. The directions are related in this way. If your thumb is pointing in the direction of the magnetic field, then your four fingers will give you the direction of the current. Even the opposite is true. If you have a current, you just curl your fingers. You curl your fingers in such a way that they are following the current. Then your thumb will give you the direction of the magnetic field. Okay, coming back. In this problem, what is happening? As the wire moves towards the right, magnetic flux decreases in the magnetic flux decreases. Yes, that is obvious because number of field lines passing through this area is decreasing. So what will the wire do? The wire will induce a current in such a way that this uh, this is opposed. So how do you oppose it? You increase the magnetic flux in the same direction. How do you increase the magnetic flux in the same direction? Take your right hand thumb and point it in the direction in which you want to increase your magnetic flux, which is this one. Place your thumb here. After you place your thumb here, now you have to just curl your fingers. If you curl your fingers, you will get the direction of the current. So here the direction of the current is anti-clockwise direction. So current must be induced in this direction alone, so that this change in magnetic flux is opposed. In the other scenario, the magnet itself is moving to the left. If the magnet itself is moving to the left, it has the same effect because magnetic flux is decreasing in this direction. So in order to oppose the change, a current will be induced in such a way that that change in magnetic flux is opposed. So how do you do that? It means magnetic field should be in this direction. That would mean your thumb should be in the same direction. And now you curl your fingers. If you curl your fingers, you will get the direction of your induced current. Okay, that is fine. Now we should be able to answer questions on the direction of induced current and all that, change in magnetic flux and so on. Okay, these two are different cases because, okay, fine, that is fine. Moving on. Uh, Different cases because here the wire is moving and then you got EMF. Here the magnet itself is moving, still you got EMF. But it doesn't matter, right? Because both of them are they're doing the same thing, which is change in magnetic flux. So irrespective of what moves, you will still get an EMF. But if you look carefully, like mathematically or whatever, conceptually, here charges are not moving in the second case. That would mean FB will be zero because FB is Q into V cross B. So FB is zero in this in the second case. It means whatever current is there. Now, what is current? Current is basically flow of charges. It means charges are moving. Why will charge move? If it experiences some sort of a force. But here, magnetic force is exactly zero. That means there is some electric force being generated somehow. Somehow, in the sense we know it is now electromagnetic induction. So, if you have electric field, the electric field came out of nowhere. I did not place any battery. I placed nothing. It's just moving now. And I know magnetic force is zero. That means the only other possible force is electric force. So that is an interesting observation here. There is electric force, and if there is electric force, that means there is an electric field, and essentially there is a potential difference. And we know what is a potential difference. The potential difference is uh, uh, here, the EMF, they have the same units, right? So this is how you connect the dots. So this EMF will give you not essentially potential difference, but we'll not go into detail. We'll just see. But something related to electric field is happening here. That's it. Magnetic force is zero. Due to electric field, all the charges are moving. This can be simply explained using EMF, but if you go deep down, you will understand. Only electric force is at play here, no magnetic force. Okay, we are going into the math now. Uh, they won't ask you derivation, so here what you have is you have the integral form of this epsilon is nothing but E dot dl, right? Do we have that? No, we don't. Fine. Uh, Fine. So just keep in mind epsilon is E dot dl. Dl is basically the entire loop that you're considering. So in this case, it was this one. This electric field is the electric field that I'm talking about. Due to electromagnetic induction, this electric field came into existence. So you have epsilon equal to integral E dot dl is equal to minus d phi by dt. This is the integral form, and then you have the differential form. So what does this mean? If magnetic field is changing, then you're inducing an electric field. So that is where the electric field came from. So two formulae, one is integral form and the other is differential form. This is the magnetic flux I was talking about. Stokes law, gradient theorem, Gauss divergence, all of these will not leave you. Maybe just see how to use them. Nice. So curl of electric field is minus dou v by dou t. Fine. So whenever there is a change in magnetic flux, you will generate an EMF, and that EMF is equal to this. This is called Faraday's law. Lenz's law is basically about this minus sign. So if there is a change in flux, that flux, the change will be opposed. So opposed is like it resists or it hates it or whatever. Resists basically. Opposes. So this minus sign is basically Lenz's law. This entire thing is basically Faraday's law. So Faraday's law is that if through any closed loop, if the magnetic flux changes, then you will get an induced current in such a way that the change in flux is opposed. The speed of the conductor will affect the EMF induced because EMF is essentially this. So if you move the if you move the wire too fast, it means the flux is changing too fast. So rate of change of magnetic flux will be a larger number. So EMF will also be high. So if the speed is higher, you will get higher EMF, and higher EMF corresponds to greater current. And if you move it slowly, it means the rate of change of magnetic flux is a small number. So you'll get a small EMF. If you have a small EMF, you will have smaller current. Okay, now you have some mathematical problem. So the loop is going to the right. This loop is being pulled to the right with the velocity v, and x is decreasing as time passes. So if v is a positive number, then v will be equal to minus dx by dt. Because as time passes, x is decreasing. So dx by dt is a negative number. So if v is speed, so v is positive, so v is minus dx by dt. Maybe just look into this, but this is the correct expression because x is decreasing over time. So dx by dt is a negative number, but v is a positive number, so v is minus dx by dt. If x was increasing, then you wouldn't have to write this minus, but here x is decreasing. So let's see. At any instant of time, flux is basically b into the area, right? Area is hx, fine. D phi by dt is b is constant, h is constant, so dx by dt. But dx by dt is minus v because we've seen, because v is minus dx by dt. Dx by dt is minus v, so you'll get a minus v. Epsilon is minus d phi by dt, so you'll get minus of minus bhv, which is nothing but bhv. So epsilon in this case is bhv, your EMF. But the moment this loop goes out of the magnetic field, then there is no EMF. Okay, in all of these cases, you will have change in magnetic flux because magnetic field is changing, even in this case. Except in this case, nothing is moving here, so there is no change in magnetic flux. So no EMF will be here. Here there will be no EMF. But if you notice uh, in these two cases, the magnet is moving, and in this case, the loop itself is moving. So in the cases where the magnet is moving and the loop is not moving, I can directly say the magnetic force experienced by the charge carriers in the loop is zero. because they are not moving. I know FB is a Q V cross B, right? B is 0, so force due to magnetic field is also 0 in these two cases. But here the loop is moving, so V is non-zero. That would mean Q is non-zero. So that is what they're telling. In cases 1 to 3, force due to magnetic field is 0 because the loop itself is not moving. Only in case 4 the loop is moving. So that would mean velocity is non-zero, and therefore force due to magnetic field is also non-zero. You can guess the direction of the current as well. So in this case magnetic flux is increasing in this direction. So what will the loop do? The loop will try to decrease the magnetic flux in this direction. How do you decrease in that direction? You create in the opposite direction. You start increasing. So you have to increase the magnetic flux in this direction. How do you do that? Take your thumb, point it in this downward direction, and now you rotate your fingers. If you rotate your fingers, you will get uh, clockwise direction. So I will be in the clockwise direction. Case 2, nothing is happening. Case 3, as the magnet moves closer, the number of field lines will increase, and therefore magnetic flux will increase. So in order to oppose this, you have to decrease the magnetic flux in this direction. How do you decrease the magnetic flux in this direction? You increase the magnetic flux in the opposite direction. This way, you can decrease the magnetic flux. How do you do this? You take your thumb of your right hand, point it in the downward direction, rotate your fingers, you will get clockwise direction. So I will be in the clockwise direction. In the fourth case, when the loop is uh, when the loop is moved away from the magnet, the intensity decreases, right? The magnetic intensity. That would mean the number of field lines passing through the loop will also decrease. What does that mean? That means in this direction the flux is decreasing. So if the flux is decreasing in the upward direction, the opposite thing that you could do is you have to increase the flux in the direction. So that would mean if you want to increase the flux in this direction, you take the thumb of your right hand, point it in the upward direction. Now rotate your fingers. You will get anti-clockwise direction. So I induced will be in the anti-clockwise direction. Okay. This is EMF. Examples you can. Okay, fine. Let me just go through this. Um, okay, it's like okay, you have some material with magnetization M. Fine. So it would look something like this, no? So as the cylinder moves closer to uh, the loop, what will happen? So magnetic field lines keep increasing. The number of field lines passing through the loop will keep increasing, and at one point it will just be like this, right? It will go inside and finally it will come outside as well. So what is happening? Fine. So initially, what is happening is the number of field lines passing through this area of the loop keeps increasing. The number of field lines keeps increasing, and in between there will almost be no change, and at the end it decreases. So I think that is what they want to tell. The flux is basically a number of field lines passing through the area, right? So initially it increases, 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 and it stops because it, it's the same line. You will be uh, this loop. The same number of lines will pass through it because in the center it's almost constant. If I have a magnet in this region, it's almost parallel. You don't find any change. The number of field lines passing through the loop will almost be same. So the flux is like constant. But finally, when the magnet moves out of the loop, when the loop is here, when the loop is here, and as the magnet goes to the left, the number of field lines passing through the loop will decrease. So flux also decreases. So flux initially increases, stays constant, and then decreases. And this, I think, this is as time passes. How much is the uh, EMF? EMF or which one? D phi by dt. Let us try to understand what is d phi by dt in this case. If I plot d phi by dt, d phi by dt is basically the derivative, right? So here I had a positive slope until here somewhere I had a positive slope. No, I still have a positive slope. So positive, 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 positive. Then negative, 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 negative. So it's like if you have a positive slope, okay, fine. So positive slope means initially it's increasing and then it's still positive. It is maximum here. You have the maximum slope somewhere over here. Somewhere you reach the maximum and then it's still positive but it's moving towards zero and then slope becomes zero. So you have nothing there. Finally it starts getting negative, 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 and then you will reach maximum. Finally you will move towards zero. The slope becomes zero at the end. So you will get this. You'll get something like this. But EMF is minus d phi by dt. So this will be reversed. So you'll get this. So approximately we can draw the graph. So here slope will be maximum. Here slope will be minimum. So that is where you have the slope will be maximum. Here also you'll have slope minimum. Until some place here slope is positive. For some place the slope is negative. So that is what we got. We got positive slope, we got negative slope. So yes, so Lenz's law is basically the minus sign. It opposes a change in magnetic flux. The current is induced in such a way that the change in magnetic flux is opposed. And yes, since current is induced, I told you, right? If there is a current, if there is a current, the current will have a magnetic field around it. So the net magnetic field also has a direction. So if the loop is this way, just take your right hand, curl your fingers. The thumb will give you the direction of the magnetic field. So if current is induced, the magnetic field associated with that current is the induced magnetic field. So yes, uh, look at this. So you take the right hand, you take the thumb of your right hand. If it is pointing downwards, then you curl your fingers. That will give you the direction of the induced current. You can try it here as well. If you have a magnetic field upwards, take your thumb, point it upwards. It's a right hand. And if you curl your fingers, try to curl your fingers, you will get the direction of the induced current. Here also same. You take your thumb, point it downwards, then your current will be in this direction. If you curl your fingers, you'll get the direction of the induced current. Uh, it's the same phenomenon, but they just ask. It's the same phenomenon. See, there seems to be a current source, and mm, the okay. If I look at it from the top view, basically current is. Okay, let me just take it here. What is the direction of the magnetic field associated with this current? Current is moving clockwise, right? No, anti-clock. How is it going? Anti-clockwise. So if you take your fingers and curl them along the direction of the current, that would give you the direction of the magnetic field. The thumb will give you the direction of the magnetic field when you curl your fingers of the right hand along the direction of the current. It will be this. So the magnetic field associated with this solenoid, the direction will be in the direction of the magnetic field will be in this direction. So what you do is you simply place a metallic ring on top of this solenoid. The experiment is this. Initially, the current is turned off, and now you place the metallic ring. After placing the metallic ring, when I switch on the current, switch on the power, what will happen? Current will start flowing, and this B will be generated, but it won't be generated in an instant, right? From zero, it is moving to B. That means in that short period of time, the magnetic flux passing through this ring changes. So there is a change in magnetic flux in that short interval of time. After I switch on the current, current will start flowing, right? So magnetic field will move from 0 to B. So there is a change in magnetic flux uh, passing through this what? This metallic ring. So in order to oppose this, why is it opposing? Because electromagnetic induction. So this magnetic ring, in this magnetic ring, a current will be induced in such a way that this change in magnetic flux is opposed. So what is happening? Yeah, as time passes, magnetic flux is increasing in the upward direction. So you have to oppose this. How do you oppose this? How do you oppose this? You decrease the magnetic flux in the wait, in the upward direction it is increasing. So how do you oppose it? You decrease it in the upward direction. How do you decrease it in the upward direction? Basically you increase it in the downward direction. So if you're increasing it in the downward direction, it means take your right hand thumb, point it downwards, and then curl your fingers. You will get your direction of induced current, which will be clockwise direction, and the magnetic field associated with this metallic ring will be downwards. But if you notice, this solenoid's magnetic field and the ring's magnetic field are in opposite directions. That means these two will repel each other now, and since they will repel, this metallic ring will start flying in the air. It will just pop. It will just go into the air. So the experiment is this: as soon as I turn the power on, the metallic ring will start flying. It will just go up into the air. So the ring jumps up. So jumping ring example. Why is the ring jumping? Because you can write this explanation in the short instant of time when uh, basically, see, magnetic flux is changing from the time the switch is turned on. Magnetic flux is changing. Therefore, an EMF is induced in such a way that the change in magnetic flux is opposed, and the direction of the magnetic field associated. So, the direction of the induced magnetic field is opposite to the direction of the magnetic field of the solenoid. Since these two directions are opposite to each other, then they will repel. So, since they repel, this metallic ring will fling into there. It'll just jump. You can write whatever reason you want as long as it is logical and coherent and consistent. It is fine. Okay, inductance. Okay, so you have a current carrying loop. You have one more loop, but no current as of now. Since if you have a current carrying loop, you also have a magnetic field associated with it. So take your right hand, curl your fingers along the direction of the current. Your thumb will now give you the direction of the magnetic field. So your thumb will be pointing upwards. So magnetic field will be upwards. If magnetic field is upwards, it means this is a closed loop. It has an area. Magnetic field lines of the first loop will be passing through the uh, area of the second loop. So there is some magnetic flux that is passing through loop 2. So magnetic flux, so magnetic field lines of loop 1 are passing through loop 2. That is fine. So what is inductance? We'll see. Okay, we know current I1 is in loop 1. B1 is produced, fine. So phi 2 is basically uh, flux of B1. So magnetic flux through loop 2. That this is phi 2, fine. Biot-Savart's law is mu naught by 4 pi I into dl1 bar into r cap by r, isn't it? Where r is the distance of separation. Biot-Savart's law, that is fine. B1 is proportional to I1. Okay, so they're proposing something. The magnetic field of loop 1 is proportional to I1. Yes, so if I increases, B will also increase. So that is understood. Now, magnetic flux through loop 2 is nothing but the magnetic field dot product with area. Magnetic field is basically magnetic field from loop 1. Fine. And now they're writing something else as well. They're saying phi 2 is M21 into I1. So what they're trying to say is magnetic flux of loop 2 is proportional to the current of current passing in loop 1. Why is that possible? Because I know flux of loop 2 is dependent on the magnetic field, right? So this will somehow be proportional to the magnetic field. And I know that B1 is proportional to I1, because if I1 increases, B1 will also increase. So we can say that the magnetic flux of loop 2 is proportional to the current in loop 1, and the constant is called mutual inductance. We will see what is mutual inductance. In minor two topics, we've seen that magnetic field can be represented as a curl of a quantity, and this is called the magnetic vector potential, which is a vector quantity. And we chose, here will be R. Uh, uh, we chose it to be this for some reason. Some reason in the sense, we'll come back to that. When we come there, we will see. You must recognize it in this form. This is for volume currents, but here there is a line current. So J bar d tau has been replaced with I dl bar. Yes. So this will appear later. Later, later in the sense previously, but we'll see it later. So what they're trying to show us is they want to show us what is M21. We wrote that phi 2 is nothing but phi 2 is proportional to I1, right? So after doing some math, you will see that phi 2 is there, I1 is there. So the rest of the term is nothing but M21. So M21 is here. I think basically we used Biot-Savart's law, right? We kept this B1 here. You keep, no, that's it. We just used Biot-Savart's law. In this case, okay, they just converted B to A. That is also fine. Unless you could have simply replaced this, no? What would have happened? Okay, Biot-Savart's law, you have all of this, no? You don't want all of that. Fine, fine, fine. The derivation wouldn't matter, but the thing is, you have this phi 2 is the flux, magnetic flux of the second loop is proportional to current in the first loop, and the proportionality constant is called mutual inductance. Look into the units. Inductance, I think Henry is the unit, I think. Oh, this came in the quiz, no? Inductance is a geometrical quantity. This came in the quiz. And you can reverse the roles as well. So M21, M12, they're the same thing. So what you can do is you can loop 2 can have a current, and you can calculate what is the relationship between the flux, magnetic flux passing through loop 1 and current passing in loop 2. You will get M12, but it's the same thing. M12 is equal to M21. Now, now they're considering something. Now, instead of there being a constant current in the loop, here there's a loop, here I1 is there, no? Let's say I1 is changing If I1 is changing, that means B B1 will also change. If B1 is changing, that means the magnetic flux passing through loop 2 will change. So, and we know this, wherever there is a change in magnetic flux, EMF will come into picture. So they're considering some change in I1. If I1 changes, B1 changes. If B1 is changing, phi 2 will also change, because we know phi 2 is B1 dot dA2, and therefore EMF will be there. How much is the EMF in loop 2? So how much ever is the rate of change of flux with a minus sign, that will give you EMF. And rate of change of, and we know phi 2 is nothing but M21 into I1, right? So d5 by dt will be nothing but M21 di1 by dt. Minus sign, so minus sign. So this will be the induced EMF in the second loop. And what does it mean? If there is an EMF in any loop, that means a current will be generated, right? So in loop 2, now a current will be flowing. So this is their observation. The loop 2 is not connected to any battery, nothing is there, but now a current is in the loop. That is the observation. Why is this happening? Electromagnetic induction. So that is what is surprising. That's why exclamation mark. Anyways, so if current is if the current is changing in loop 1, only then magnetic flux passing through loop 2 will be changing, and therefore there is EMF, and therefore induced current in loop 2. Mm, fine. Now one more observation. If in loop 1 itself, we said that the current is changing, right? So if current is changing in loop 1 itself, so even the magnetic flux of the loop 1 itself, even that will change, because B1 is changing. If B1 is changing, phi 1 will also change, because phi 1 is nothing but B1 dot B1. So magnetic flux passing through loop 1 itself will change, because B1 is changing. So what they try to do is they try to write this as something proportional to I. So magnetic flux of the same loop is proportional to I. So and the proportionality constant that they kept is L. So L is called self-inductance. So the EMF in that case will be nothing but just d phi by dt with a minus sign. So minus L di by dt. Back EMF, because uh, like the change in current, the, due to the change in current in loop 1, now one more current is induced. So it's like, what is the loop trying to do? When the current is changing, the loop is trying to oppose the change in current. So that is there. So that is why back EMF. Okay, interesting. We'll come to Maxwell's equations. Force due to electric field, force due to magnetic field. Fine. Integral form of Gauss law, differential form of Gauss law. Fine. Curl of electric field is zero. Yes. This was before minor one. We discussed why curl of minor before minor one. I think during minor one. Why curl of electric field is zero. So what they're saying is, if they try to solve these equations using some boundary conditions, then they will get Coulomb's law and principle of superposition. Like if you're very far away from any source, then electric field is zero. There is no effect of any charge density. Okay, magnetostatics, let's see. This is Gauss divergence theorem, right? Divergence of B, yeah, Gauss divergence. Divergence of B is zero because there exists no magnetic monopoles. This is Ampere's law. Fine. There is one more form, right? This is the differential form. The integral form of Ampere's law is you just apply uh, what theorem? Stokes theorem. If you apply Stokes theorem, you will get B dot dl. On the RHS, what will you get? You will get mu naught I. So this is the integral form of Ampere's law. B dot dl is mu naught I. Fine. So they're like if you solve these equations by applying this boundary condition that at infinity b is zero, then you will get the Biot-Savart's law. Apparently, we are not deriving anything; we're just reading. And Faraday said that there is a EMF, right? EMF is this one minus d phi by dt. Integral form, differential form. Nice. So they're just trying to write everything in one page. Magnetic monopole zero. Change in B will induce an electric field. Fine. Now what they're trying to do? Okay, they have this. They're trying to take its divergence. Fine. So steady current. Steady current in the sense there is no accumulation of charges. Or not accumulation of charges. By this I mean uh, the current is constant, which means charges don't accumulate, but current is not changing. It's steady. It's just constant. When current is constant, there will be no divergence of J. What is J? J is the J is nothing but di by dA, right? What do you call this? Uh, Current density, something. It's called something. Current charge density, volume current density. I think it's called volume current density. No, it's. I think it's called volume current density. And when uh, what do I mean by steady current? It means at a point inflow is equal to outflow. It means there is no accumulation of charges. If there's no accumulation of charges, if inflow is equal to outflow, divergence will be zero. So that is why divergence of J is zero. If divergence of J is zero, what is happening? Curl of B is zero. Fine. So basically, if divergence of J is zero, then curl of B has to be zero. Fine. There is something called continuity equation. It was there. I think this was introduced in the previous slides. So we'll not look at the derivation, but this is called the continuity equation. But for steady currents, there will be no accumulation of charges. So this value is going to be zero for steady currents. Only steady currents. But let's say we are not dealing with steady currents. Then what will happen? Okay, this person is using Gauss's law, right? We know divergence of E is rho by epsilon. So he's replacing rho with epsilon naught divergence of E, and then he's taking the divergence operator outside. So you have this. and now you have something strange looking. So if you don't have a steady current or something like that, you can't simply say divergence of J is zero. Divergence of something else is zero, and the something else is this one. So that is what not Ampere, that is what Maxwell is trying to tell, I think. Yes. He just added this continuity equation. This was missing from all the previous things. He's using this continuity equation and then is trying to change something. What is he trying to tell? He's trying to tell that divergence of this quantity is zero, not only this one. This is zero for steady currents. What if there are no steady currents? Then you have to use this. So why does the Ampere's law change? Because we are okay. We are trying to modify this. Right. So now if I take the curl of this one, curl or divergence? Divergence. If I take the divergence on both the sides, Maxwell is telling this is zero. Fine. That would mean curl of magnetic field is also zero. Hmm. Anyways, Maxwell thought about something and then he added this extra term over here. So this is called Maxwell's correction. And if you notice here, if E is changing, then B is also changing. So previously we saw that if B is changing, then if B is changing, then E is changing. So the thing that was missing from these equations is this part. If E is changing, then B will also change. So that part Maxwell introduced. If E is changing, B is also changing. And if you remember, the electric displacement is nothing but epsilon naught E plus P bar. Uh, let us consider P to be 0. So they're just replacing E naught epsilon naught E bar with D. When does P become 0? It's like if you don't have any polarization. P is polarization, right? If you don't have any polarization, P becomes 0. In in what cases can polarization be 0? Let's say you're talking about air or vacuum. There is no polarization there, so P can be 0. P is 0 there. Or else the original Gauss law was this. The Gauss law using dielectrics, it was divergence of D is rho free. But since there is no polarization, rho bound is essentially 0. So rho is nothing but rho free plus rho bound. Since we are considering P to be 0, rho bound will also be 0. And therefore rho is rho free. So that's why this is here. But the original Gauss law is this one. You will notice this in the minor 2 portion. Gauss law using dielectrics. So okay, this person is changing Gauss law so much, Ampere's law so much. Fine, he's changing, changing, changing. Okay, finally he's calling. What is this? Okay, so new term. Now this is called displacement current. This D is electric displacement or displacement vector, whatever you want to call it. The rate of change of electric displacement is the displacement current. Misnomer because it's not exactly current. It's like uh, it's like current. It's talking about the rate of change of electric field. Its units are not amperes. So displacement current is called displacement current, but its units are not amperes. That's why misnomer. Not exactly a current, but it's called that way. So this is the corrected form of Ampere's law. So Ampere's law with Maxwell's correction. You should know what is displacement current. It is this one. And keep in mind we're considering polarization to be zero. I don't think they will give you a question in which polarization is non-zero and then they'll ask you to do all of this. Then you'll have to be careful. But there'll be no derivation, so you can be happy about it. It should be row free, but since P polarization is considered to be zero, I can just remove this. Okay, no monopoles, that is fine. Change in B will result in change in E. This is Ampere's law with Maxwell's correction. A new term got introduced. So this is displacement current. Yes, so they have to consider P to be zero, or else all these equations are horrendous. We know D is this one, which is also equal to epsilon naught. So if P is zero, then epsilon is epsilon naught. That is fine. This is also fine. This is also fine. This is Ohm's law. There's this entire thing, if you know, if you notice, if you this is nothing but mu naught, mu r, h. All of this was there in minor 2 syllabus, I think. 1 plus chi m h mu naught h plus mu naught chi m h, which is nothing but mu naught h plus mu naught m, because m is chi m h. So many things are there. You can just see that this is the permeability of the medium. This is permeability of free space. This is relative permeability. This is susceptance. This is B is actually magnetic flux density. H is actually magnetic field intensity. Fine. M is the magnetization. It came in one of the questions, no? The question we had M. It was passing through a loop. So M is magnetization. In other words, magnetization is nothing but magnetic moment per unit volume. Like how we have polarization, dipole moment per unit volume. Oh, nothing is here. Fine. Let's see what is there. All of this is fine. Oh, wait, wait, wait. Did they introduce anything? Okay, so, okay, fine. Now they're trying to scare you people. Rho is zero. Fine. That means there is no charge density anywhere around. Essentially, J is also zero. No current is not there. No dielectric medium. I know B is uh, mu h, or else I can write this as or else Can write this as, okay, I can write it this way. Fine. So we know that divergence of B is zero. So divergence of B is nothing but mu naught. Like how they considered P to be zero, you also consider magnetization to be zero. So that would mean in that special case, B bar is nothing but mu naught H bar. This is when magnetization is zero. So I can replace B bar with mu naught H bar. So that is how they got divergence of H bar is zero. And here there used to be a B, right? Curl of electric field was minus dV by dt. They replaced B with mu naught H bar, and that is why mu naught came here. Considering magnetization to be zero, lot of assumptions. Same story here. We had curl of magnetic field to be what is it? Mu naught J bar plus the displacement current. They consider J to be zero if there is no current around. So there is no current, there is no charge. So charge free, current free. Uh, Current free means there is no J, so this is zero. And they're replacing B with mu naught H bar. And displacement current is essentially epsilon dE by dt when P is zero. So finally, if you simplify everything, you will get this one. So they're just rewriting the old ones in new forms. That's it. So taking curl of 3 is curl of electric field. There is a formula for this. So curl of a vector field is nothing but gradient of divergence minus the Laplacian. So this is the gradient of divergence minus Laplacian. And curl of H is already the fourth equation. So they substituted this here. So after some simplification, what you'll get is this one. This is nothing but the wave equation. Okay, so they're not considering epsilon naught here, they're considering epsilon. That would mean, wouldn't that mean P need not be zero? Because I know D is epsilon E bar, which is nothing but epsilon naught epsilon R E bar, which is nothing but epsilon E bar plus P bar. So if P is non-zero, then D can be epsilon E bar. Because they said dielectric, so P can be non-zero, and if P can be non-zero, but if P is non-zero, you might have a charge distribution. Mm, because if P is there, rho need not be zero. Fine. So if P is zero, then epsilon has to be epsilon naught. But anyways, we'll just go on with this. We'll get on with this. So my concern is if you're writing epsilon here, it will essentially be epsilon naught. But we'll move ahead with this. So this is the wave equation which we got from Maxwell's equations. So what are the assumptions that we took? Uh, it is moving in a medium. There is no current. There is no charge. So charge free, current free, homogeneous and linear in the sense these are not changing in the medium. U naught is a constant. The uh, permittivity is constant as well. Permittivity, both of them are constant. A wave equation of a vector field. Let me just write this. So f bar can be any vector field. So this is the wave equation. So that would mean in our case where F is electric field, we'll see, we'll come to that. We'll come to the speed of light, that this is how we'll derive the speed of light. Okay, wave equation. To find the solution of the wave equation for monochromatic waves. That means monochromatic means you have one color. If you have one color, that means you have one frequency. So if you have one frequency, you'll have one omega. So what they're trying to do is they're trying to use something called variable separation method. What you do is you have a function in two variables, right? So you write it as a product of two other functions, and each of those functions is dependent on only one variable. So you have a function depending on these. R is the spatial part. You're moving here and there, right? So that is the spatial part, and the other function is dependent on the time. So this is called variable separation. Maybe you could just you don't have to look into it. Maybe interested people could look into it. So the process here is variable separation method. So spatial part I have, and temporal part, basically the time part. So I have two parts here. Time dependent, in other words. So plus or minus for time dependence is completely arbitrary. But in the class, what we are using is we are using the minus sign. So we'll go ahead with the minus sign. So why is electric field a function of space and time? Because the electric field, okay, monochromatic wave, the electromagnetic wave that we're going to talk about, it's moving in space. It's moving across space, across time. So it is a function of space and time. Mm. And if you notice, we're involving imaginary numbers, right? So um, but the real world, there's no imaginary dimension or something, right? It's just there to help us out mathematically. So the real part of this uh, electric field will give us the real value. The imaginary value is just there to help us out. So the physical, the real electric field is the real part of this equation. So how do you say this? Because if I can rewrite this one, right? I can rewrite this as a cos omega t minus phi plus sine. If I take the real part of this, I will only get this part. So that's why it's telling that the electric field is proportional to the cos part. Fine. Now what they're trying to do is now that I have assumed a form, the solution that we are assuming that our solution will look like this. So just go and substitute in this one. After substituting, some simplification you do, you will land up at this equation. And in this equation, there is no time variable. So the solution of this equation will tell us how will ES look like. So the spatial part of the equation, how will this vector look like? The solution of this equation will give us that. Now they're telling that consider our wave to be a plane wave. Now plane wave is basically this one. It looks like this. This is a plane wave. So you have a plane. It's just oscillating to and fro. It's propagating in one direction. So direction of propagation is this one. How do you know that it's a plane wave? It means uh, its amplitude is like at any given point its amplitude will be the same. For example, if I at any point in the plane perpendicular to a specific direction. Fine. So if I look at if I look at a direction in this direction, the amplitudes are same in all the planes. It's like the amplitude doesn't change or something. Along with the amplitude not changing, you also have this the the phase between each of the plane waves. They are constant. So it's not like, let's say this is at t equal to 0, wave is here. At t equal to 1, the plane is here. At t equal to 2, the plane is here. At t equal to 3, it is here. And suddenly at t equal to 4, it is here. Here the phase is not constant. But for a plane wave, it should be constant. The phase between the planes, it is constant. Then this is a plane wave. But this is not a plane wave. This is a plane wave. Phase in the sense, mm, this is called the phase, the one inside the cos, or the the coefficient of I. This is the phase. No, this is the phase, or whatever is in the cos, that is the phase. Phase difference is if you take two planes and take the difference between their phases, you will get phase difference. This phi is called phase angle. Like if you're already starting from angle phi, then that is the phase angle. So okay, fine. So I was the direction of propagation in this case is z. So all the planes are uh, moving towards the z direction. So the spatial wave is a function of only z, because the plane is moving in the z direction. It's not moving in the x or the y direction. It's simply moving in the z direction. So the spatial part of the electric field is only a function of z. So this vector is only dependent on z. There is no other variable. There could be constants, but the only variable is z. About the plane waves, you could think of it like this. So if you have a torch, not torchlight, okay, let's say you have a laser or something, but okay, fine. Let's just assume you have a beam of light that is not uh, dispersing or something. It's just moving. It's like a cylinder. It's going like this. So you can consider each of them to be. You can slice them up into small planes. So you can consider them to be plane waves. So they're all planes. So plane wave. They're moving in some direction z. So you have a beam of light. So and at every if I take a plane, the amplitude of the electric field in each of those points is the same. So that is what they're trying to tell. If I take any z value on that plane, the amplitude is same for all the points in the plane. Essentially, the spatial part of electric field is a function of z. So if Es is a function of z, then the Laplacian, how does it look like? It's going to be like dou square by dou x square plus dou square by dou y square plus dou square by dou z square. These things will not be there because I know now Es is simply a function of z. So my Laplacian will directly become z, dou square by dou z square. And if you solve this equation, it looks like SHM equation, right? SHM equation. D square y by, maybe there was time there. I don't remember, but it looks like that. So the solution to this equation is something that looks like this. Es is a function of z, so there's only z here. So this is some function of z, and you have a vector because this is a vector quantity. So you have some constant vector. That is fine. So omega is there, the epsilon is there, permeability is there, everything is there. Fine. Now if I try to substitute the solution I got in Gauss's law, we saw that this is essentially row free, but since p is 0, row is row free, so that is why they're omitting this. And d is epsilon naught e, so I can change this to epsilon naught e. And since there is no charge anywhere, so rho is 0. Epsilon is constant, that is gone. So divergence of E is 0. And E is nothing but E spatial into e power plus or minus I omega t. But divergence will only affect the spatial components, because what is divergence? Divergence is basically this, right? This is divergence. There is no derivative with respect to time. So this is considered as constant. It comes out of the equation. 0 is there. It also goes away. Finally, you get divergence of E spatial is 0. Now, if you try to substitute the solution of E spatial in this equation, it will look like this. So you're what are you trying to do? And we know that E spatial is simply a function of Z. So there will be, these terms will not be there. Only this one will be there. So you have this ESZ, we know what it is. So it will look like this. Okay, fine. There is ES here, there is ESZ here. What is happening? I can write my vector ES as x cap E SX plus y cap E SY plus z cap E SZ. I can write it like this. I'm just splitting my vector into multiple components. So if I take the divergence of ES, what is happening? I will get dou ESX by dou X and dou ESY by dou Y plus dou ESZ by dou Z. But I know my ES is a function of Z. So this will be 0, this will also be 0. And if divergence of ES is 0, that means now my derivative of ESZ must be 0. I can differentiate my ESZ. What will I get? I'll get this one. I just have to differentiate this. E naught bar is a constant, so that is not a problem. So if this has to be 0, I know omega is non-zero, epsilon is non-zero, mu naught is non-zero. So ESZ must be 0. So if ESZ is 0, that means my ES will not have a Z component. There is no Z component for ES. That would mean my ES will only have X cap and Y cap components. So my ES will only have an X component and a Y component. There is no Z component. So this was my E naught bar. Similarly, if you solve for B, you will get something like this. If you want to find the magnitudes, that is simple. You can just use this one. E is VB or CB here. This came in the quiz. They were like, what is the ratio of the amplitude of electric field to the amplitude of magnetic field for an electromagnetic wave? It is simply c, the speed of light. Mm, so I think they applied the same process. This is for This is B spatial, magnetic field spatial component. So if I know E, I can find B as well. So B is nothing but E by C. If later we'll prove that C is nothing but this is C, or else I'll put V here. We'll come to this later. It's like a spoiler at this point, but I told you this will prove this. Mm, fine, you can think about this if you want to. Okay, fine. Let me just spend 1 minute. How do I write BS if I know ES? I know how ES looks like. So it is going in the Z direction. My E spatial will only be in this plane. It has no Z component. My B will be in a direction that is perpendicular to the direction of propagation as well as electric field as well. So this will give me the direction. Its magnitude is how much? Its magnitude is whatever is ES, and this is nothing but 1 by V. Yes, so that is simple done. So if BS is nothing but plus or minus, we'll see why plus or minus 1 by ES, but direction is different. So fine, beautiful. So what is happening is this has a direction that is perpendicular to uh, direction of propagation as well as the electric field itself, and its magnitude is Es. That is nice because we know that B is nothing but the magnitude of B is nothing but magnitude of E by V. So its magnitude is E. We have V as well, so we are done. So this is correct. This is not a wrong formula. Fine. Where were we again? Okay, we showed that Z has ES has no Z component. Yes, so we will be assuming time time dependence. What are we taking? Are we taking plus or minus? We are considering uh, here we are taking plus. Here, how did we take plus? How first of all, where did we get this from? Where is it? Okay, see, plus or minus was there initially, and then we have to take e power minus omega t. So later it became minus plus. So if we take minus initially, then we have to take plus later on. So we will take plus. We will take this. So that is what they're telling. So if you take the time dependence as e power minus I omega t, then positive z direction is represented by this one. So in our es of z, we will take plus here, not minus. So es of z will here plus sign will come. So that would mean this is my spatial part. Now I can substitute in the original electric field. So spatial part into temporal part. Spatial part is nothing but uh, this one, E naught, E power something, something, something. And then I have minus I omega t. I common, omega common, fine. So I can write this as E naught power I. So I can write it this way. So because we are used to seeing wave equations in this format, right? Omega t minus kz. At least I am used to seeing omega t minus kz. So I'll write it this way. In case this is for a wave traveling in z direction. What if the wave is traveling in some 3D direction? What do you do? So that is simple. So you will have uh, E is nothing but E naught e power minus I omega t minus k bar dot r bar. K bar is nothing but it is called the wave vector. Its magnitude is 2 pi by lambda, and its direction is the direction of propagation. R bar is nothing but x x cap plus y cap plus z cap. That is essentially R bar, right? So if you have any wave that is moving in some direction, you can use this. And if it's an electromagnetic wave, we have some other formula as well. C is nothing but lambda mu. This will help us. Okay, now we are trying to find the speed of light. Fine. So phase is nothing but the one that is inside this. The inside part is the phase. So, and k was this one, right? K was under root epsilon mu naught. This was k. So kz minus omega t is constant. So this is phase. The coefficient of I is the phase, and for a plane wave, phase is constant. So phase is constant. Fine. So if I differentiate it, constant will become zero. So what do you get? dz by dt is something like this. What is dz by dt? dz by dt is the speed, the rate at which z is changing. So in free space, epsilon is epsilon naught. That is fine. So in free space, this is the speed. If you substitute the constants, you will get your speed of light. So this is what I was trying to tell here. We will we stored that c is this one for a plane wave. So light is a you can consider light to be a plane wave. Okay, where am I? Fine. So this is an electromagnetic wave because you have electric fields and magnetic fields oscillating. Fine, fine, fine. Yes, so k is the wave vector. K is the wave vector. So if k is the wave vector, I can write it in terms of its components. I can write it in terms of its components. If I take the magnitude and square it, then you will get kx square plus ky square. Now they just wrote the magnitude, but in a different form. So there's nothing new to remember in this. And I know the magnitude of k. It's 2 pi by lambda. Since whole square, so square. Where lambda is the wavelength of the wave. Fine, so we got this right. I would write it this way because I feel comfortable writing it this way, but you can remember it however you want. Omega t. Wait, what? Shouldn't there be a minus sign? Now it's all arbitrary, but some books will have minus sign, some books will not have minus sign. But we will consider this one. And k bar is nothing but kx x cap, ky y cap. So they just wrote it there. And if they take the dot product with r bar is nothing but x x cap plus y cap plus z z cap. So you'll have kxx, kyy, kzz. Fine. That is also fine. I would prefer a minus sign. So this was I talked about this one, right? I wrote in terms of f. I wrote this in terms of f. So if the f was e, then this is the story. In one dimension, this will be nothing but you only have one variable. You don't have to write the Laplace here. Our plane wave that we've been using, it is a one-dimensional wave, so that is one-dimensional wave in the sense it's moving in one dimension. So we can use this. Like this will satisfy not this one. This is 3D. The previous one, the one in the previous slide, will satisfy this one. If you have a wave that's moving in 3D, just plug this in the original equation to show that it is satisfying the wave equation. This is like the real part of electric field. That's why you have a cost term. If you take the real part of this one, you'll get a cost term. Here, taking minus or plus wouldn't matter because that will only affect this one, cos plus or minus I sine. So minus or plus here will only affect this. It will not affect anything else. But what we are doing is we are taking a minus sign because we assumed time dependence to be negative, right? Here minus sign is missing because t should have negative minus 1 as a coefficient. Here t has a here t has minus 1 as coefficient, so this is fine. This is fine. This is not fine. Minus sign is missing. So here they're applying boundary conditions. It's like at t equal to 0, I want uh, something to happen. What do you want to happen? What does it want to happen? Okay, now they're not okay. They're not doing boundary conditions. They're just drawing the wave at this point. So at t equal to 0, your wave, your physical electric field will look like this: a cos kx. Fine, you have this thing. Fine, and after some time, so delta t, it's going to look something like this. So they drew one more wave. So it's like this electromagnetic wave, this sinusoidal wave. It's traveling to the right. Okay, phase change. Phase change. So by how much is the phase? Whatever is inside this box is the phase. Whatever is inside the box is the change. Phase. Phase. Okay, they're like after you travel a distance of lambda, the phase changes by 2 pi. That is true, right? If you're here, it was initially 0 inside, and then if you travel the wavelength distance, the phase changes by 2 pi. So it's like phase change is nothing but uh, this is nothing but the phase difference. This is nothing but the path difference. maybe this will be helpful in what? Uh, uh, the constructive interference, that part, maybe this will appear over there. But 2 pi by lambda is nothing but k. That is fine. If you want, you can verify this. So over a distance lambda, if your path difference is lambda, then how much is the phase difference going to be? So if the path difference is lambda, your phase difference is going to be 2 pi. So nice. We can verify it using this formula. So phase difference is nothing but 2 pi by lambda into path difference. We're trying to find the time period. Time period, fine. Omega is angular frequency. Mu is frequency. Refractive index is the ratio of speed of light in vacuum to speed of light in a medium. Now, speed of light in a medium, you could have a different permeability, but then the difference is so small that it's almost equal to mu naught. So that's why they're cancelling this. So essentially, you'll get this. And what is this? Epsilon is nothing but epsilon naught epsilon r. So epsilon r is nothing but dielectric constant. So k or kappa here, kappa they're using. So here kappa is dielectric constant. Or uh, it's there. It's already there. The slides. Okay, now they're putting the other conditions. Uh, if your j is non-zero, it means some form of current is there. Some form. This is Ohm's law. This is Ohm's law, where J is volume current density, E is electric field, and sigma is conductivity. That is Ohm's law. This is This is Gauss's law, integral form of Gauss's law. But why is there a free? Okay, free because maybe this is supposed to be rho, but there is no there are no bound charges apparently. So rho became rho free, I think. So that is the intention, I suppose. This is also fine. This is also fine. You have this. Why is there no mu naught here? I think there should be a mu naught here. Yes, this is also fine. All of this is fine. They're just checking. We know all of this. No monopoles. Mm, we know this. Okay, this is the continuity equation. Because Gauss law is essentially this, right? Uh, E naught d is this one, and then Gauss divergence. This is equal to this one, and Q is equal to rho d tau enclosed enclosed. Therefore, this is equal to Okay, fine. Continuity equation. What is this person trying to write? Okay, so divergence of J free is nothing but sigma divergence of E free. Divergence of this. So J is nothing but sigma E. So okay, fine. They're just rewriting the same thing. But why are they stressing on the free part though? What is free here? It should be enclosed. Rho is enclosed. Do they mean there is no bound charge? That is what I told you just now. Does it mean there are no bound charges? Maybe it looks like it because they never mentioned anything about P. We will assume P is 0. If P is 0, then fine. Rho bound is 0. But the thing is, if you write P is 0, then epsilon will not be epsilon, be epsilon. Fine, I'll just continue with whatever is here. Mm, fine, so they replaced J with the sigma epsilon, and then you're getting dou rho f by dou t is something. Now they are putting Gauss law here. From here, you got here. From here, you got this. Fine. What do you get from this? Thus, continuity equation for free charge. Okay, so if you solve this, you'll get something like this. So what does this mean? It means as time progresses, the volume charge density is decreasing, right? Where is it decreasing? From what is it decreasing? What is the context? It's saying as time passes, something is decreasing. Okay, so let's say there is a medium in which free charges exist, and it's like when they're trying to uh, conduct electricity, they move from one place to the other. So that would mean the density at that place is going to decrease. So I think that that is the idea. In a conducting medium, if any current is passing through it, the free charges will move. They will just go along with the current. That would mean the density of the free charges in that conductor it's going to decrease over time. I think that is what this equation means, or this equation would want to say. I think that is what it wants to say. So a good conductor is basically uh, it's like the decrease is less probably, maybe that. So if I don't know what do you call this time constant, if epsilon by sigma, okay, is telling if this is a good conductor, measure of how good a conductor is. If T is large, if T is large, then if tau is large, then it means it will take a lot of time to if tau is large, then it will take a lot of time for the charge density to decrease. That means it's a good conductor, isn't it? Or is it a bad conductor? Okay, so if it's a good conductor, then sigma should be large, and if sigma is large, then tau will be less. If tau will be less, that means it will take very little time for the entire free charge to for it to get dissipated. Okay, so I understood. What I understood from this slide is if you have a conductor, uh, and a conductor means it has free charges in it. So the moment some current flows through it, the free charges should take like very little time to get dissipated. How do you know the rate of dissipation in things? You get it from here, this one. So if the conductor's free charges are able to dissipate in a short amount of time, then that is a good conductor. If it's taking a lot of time, then that is a bad conductor. It means the charges are not willing to move. Okay, see, tau is very small. If tau is very small, it means sigma is very big. Sigma is conductivity, so that is fine. So it's like you have a conductor and you have some free charges. The moment some current is passing through it, these free charges should be able to dissipate instantly, like as soon as possible. So if they dissipate, what will happen? The density of the free charges will decrease because now they're moving away. They're moving as charges. If they're able to do this fast enough, then it is a good conductor. So that is what they wrote here. So the free charges is a function of time. The volume charge density of free charges is a function of time. Initially, there is some density, but it is decaying exponentially. And this tau is nothing but epsilon by sigma, where sigma is the conductivity and epsilon is the permittivity of the medium. Since for good conductors, this happens almost instantly, you can consider rho f to be zero because the moment something happens, the density suddenly goes to zero. Suddenly, almost. Maybe you could substitute the values and see how much is uh, how much is rho rho f going to be after some amount of time, because the graph will look something like this. If it's a good conductor, maybe it'll go down very fast. So you can say for most of the time it is almost zero for good conductors or for good conducting medium. So that would mean this will tend to zero. So we're writing divergence of E as zero. No monopoles. This is fine. This is also fine. Okay, now they want to solve for the wave equation once again. Okay, is it slightly different though? Fine. We'll see. So initially we only had this one. Now we also have this extra term. Now it's a second order differential equation. You have dou square e by dou t square and dou e by dou t. Interesting. So it seems it is 1-7 now. We'll continue from here in part 2. I will stop the live stream.